Hello, I'm Joey Geraghty, and today I'll be going over my final project for Math 347, a hierarchical Bayesian analysis of lacrosse scores. My research question is, can the score of college lacrosse games be accurately predicted using Bayesian analysis? For my motivation, predicting outcomes of sporting events is a common recreation, although there does not exist many college lacrosse score prediction models. I'm interested in modeling the outcome score of lacrosse games to determine how good different teams are. The data I will be using in my analysis was scraped from the NCAA website and contains the first 377 games of the 2022 Division I men's lacrosse season. In order to scrape the data, I used Python and the beautiful soup library. A Poisson distribution measures the probability of a given number of events occurring in a specific time period. Poisson events occur randomly, but with a constant average rate per unit time. Lacrosse scoring can be modeled by a Poisson distribution because of the sport's sparse scoring and time nature. Sports like lacrosse, hockey, soccer, and water polo are sparse scoring because goals are not being constantly scored throughout a game. Often, there are long stretches of no goals. Basketball would not be an example of a sparse scoring sport because baskets are scored with high frequency throughout a game. Lacrosse also fits the time nature of a Poisson model because every lacrosse game is 60 minutes, not including overtime. Most games do not end in overtime, so it is reasonable to assume lacrosse games have a fixed time nature. The graph in the top right is the distribution of goals scored by a single team in all the data and all the 377 games collected. And the graph in the bottom right takes the mean value from the graph in the top right. So it takes the average goals scored by a team in the data and uses and then has a Poisson distribution with that same mean. As you can see, both of the graphs on the right look fairly similar, indicating a Poisson may be a good way to model goal scoring data. The graph on the left is also a variety of Poisson distributions with different rate parameters, lambda, and some of those graphs also look like they may model lacrosse scoring well, which adds to my motivation to use Poisson distribution to model goal scoring in lacrosse games. Now getting to the hierarchical model, I use two separate sampling densities for home and away goals with respect to a home and away rate parameter, lambda home and lambda away respectively. I decided to model home and away goals separately instead of together so I could see how well the model predicts the winner of games as well as the total amount of points in the game. My stage one prior for the rate parameters lambda are next. Lambda home represents the average expected goals scored by the home team in a game, and lambda away represents the average expected goals scored by the away team in a game. The log of lambda is modeled by a baseline value added to the difference between the skill values of the home and the away team. For lambda home, it's skill home minus skill away, and vice versa for lambda away. The baseline value is the log average number of goals when both teams are equal or have the same exact skill value. If two equally skilled teams played with the same skill value and there is no baseline value, lambda would be too low and not enough goals would be predicted in the model. Each skill variable represents a latent variable corresponding to the talent level of each team. So in other words, we would think the best teams would have high skill variables and the worst teams would have the lowest skill variables. Team skill values are modeled by a normal distribution. This assumes that there's an average team skill value, group skill in this example, and each team is normally distributed around this value. The rest of the hyperpriors are vague, and I kept these vague on purpose, is I don't hold strong prior beliefs of how the model should look, and I want the data to have a large impact on our posterior draws. In order to run the model, I use Jags and R, and here's my model string. All of the code in this string follows the text in the past 2 slides. After running the model, here are trace plots in MCMC, or trace plots and autocorrelation plots for all of the variables. In the top left corner, I have the skill 2 variable, and I only included the skill 2 variable, even though there are 73 skill variables, one for each Division I college lacrosse team, because all of the trace plots and autocorrelation plots for the skill variables looked approximately the same, and it would be an eyesore to keep all 73 plots in these slides. All of the trace plots for all the variables appear to have no pattern, which is good. That indicates or is a partial indicator of convergence of the MCMC chain. The autocorrelation plots have some slight positive and negative correlation, but it doesn't appear like they have anything too extreme. This highlights some information I already mentioned. Also, the effective sample size values were all at or near 5,000, which is also a good sign of convergence. I did not run the chains any longer to try to make the autocorrelation plots look perfect, because if I was running the change any longer, the Jags model would start to crash on my computer, and I did not have the computational power on my computer to run the Jags model longer. But I think the chain reasonably converged for my problem. In order to test how well our model compares to the real data, I performed a posterior predictive check. First, I took draws of each skill value and the baseline value from the MCMC simulation. So each skill value, that's for all 73 teams. Then I generated random draws from a Poisson distribution with the rate parameter as the exponential of the baseline and the difference between the home and away skill levels. The exponential accounts for the log of the rate parameter being equal to the baseline added to the difference in skills. Then the difference in skills depends if we're predicting the home goals or the away goals. I use these simulated values and compare them to the actual data to perform my posterior predictive check. And just some general thoughts from the posterior predictive check. About 95% of the actual scores from the game data fell within a 90% credible interval of the predicted scores, and 97.6% of the actual scores fell within a 95% credible interval of the predicted scores, which is pretty good. Also, the model predicted 62% of the game winners correctly, and this was done for all 377 games. We predicted, we took the skill parameters and we predicted the score of the game 5,000 times. And then we determined what percent of those games we actually predicted the correct winner. And now for a more specific example of the posterior predictive checks. We can see we compare the one single game, Ohio State versus Johns Hopkins, and the graphs from left to right include a histogram of predicted home goals, predicted away goals, and then the predicted goal differential. The red line on the graph shows what the actual goals were, or goal differential from the actual data. So just from the graphs, it seems like they reasonably match our data point. And if you look at the actual score compared to the means of our predicted scores, it's relatively close. And it predicts the correct winner, Ohio State. It also predicted Ohio State would win 67.8% of the time, which seems reasonable. They also calculated two 90% credible intervals for each team. And as you can see, the spread of the credible intervals is fairly large. There's large variability in predicted goals scored, but this may be a good thing, because this year in college lacrosse, there's a lot of new rules, which has definitely increased the variability in goals scored. So it's not completely evident if that large variability is a good or bad thing. Another more specific example, Maryland versus Princeton. So you can see the red lines of the actual data match the histograms fairly well, again. And if we look at the actual score and the mean predicted score, it does a fairly good job of predicting the score, predicts the winner, and does a pretty good job predicting the win rate. So overall, I would say the model is pretty reasonable compared to the data. And then if we look in the model in more detail, for each game, if you take the actual goal differential and subtract it from the predicted goal differential, and then take the mean of that value, you get about 1. So this means on average, the actual goal differential in each game was more than the predicted goal differential, meaning the model predicted on average games to be closer than they actually are. And this could potentially be due to shrinking/pooling effect on the skill values. If all the skill values were pulled together, this would mean all the teams are more closely aligned in talent level, which could potentially make the scores of all the games a lot closer. And in order to change this, we may have to change the variability in team skill levels. And this could be done by increasing the group sigma hyperparameter, or in our model. Thank you for listening, or for future work. So more things I would like to do was have more specific priors relating to team statistics. So after looking at this model, I think I could have better individual priors for each team's skill level, depending on specific team statistics like goals scored per game and goals allowed per game, shooting percentage. And another interesting thing to do was take this model and test it on data for previous years and see how those models compare to this one, as there's been significant rule changes in college lacrosse over the past few years. So the game has changed. So how the models are predicting how many goals are scored in a game could change a lot. Here are some citations that really helped me in my project. Thank you very much for listening.